just getting, okay, it's recording. Okay, maybe you should start.
Okay.
Okay. Assalamualaikum and good afternoon, everyone. So welcome back to another session of the UPM Physics Department seminar. So today we are honored to have Professor Kwek from CQT and NTU. Maybe I should read a few things about him. Professor Kwek is currently a principal investigator at Center for Quantum Technologies, CQT in NUS. He's also a co-director of the Quantum Science and Engineering Center at NTU. He's also the Deputy Secretary General of the IUPAC and many other. Maybe I should not read it all. Okay, and he has been active, very active. He has hundreds of publications, so I will not read all the things over here. So, but perhaps I should also mention that he was receiving a laureate of Scientia Vinces Award from Republic of Sakha, Institute of Physics Award, President Award, National Science Award, and he's currently the editor of AVS Quantum Science and Physical Review A, editor of Entropy and International Journal of Quantum Information. So I think let you start. Okay.
Thank you, Hisham, for the invitation to give a talk at the UPM Physics Seminar. Today I'm going to talk a little bit about what research that I've been working on for the last maybe 15 years or so. It's the experimental progress in this direction has been slow, but nevertheless, some of you may have heard about some of the work that I've done or other people have done in this area in other talks. And you may have seen some of these slides, but in any case, let me reiterate. So let me do a comparison between the so-called new term, which is Atomtronics, and contrast it with electronics. Now, in electronics, you have chips that are whose carriers are electrons, and you have semiconductor materials, typically silicon based, and you operate with electrical potential. Now, in Atomtronics, you change the carriers to atoms or ions, and they operate and they get trapped within not wires, but optical lattice, and they move around because of the chemical potential of the atoms. Now, atoms are chosen typically because atoms are identical. They are very stable. Typically, most of atoms operate in the quantum regime, and they have diverse functionalities. There are properties that are distinctly different. Some are bosons, some are fermions. So atoms in optical lattice is somewhat like this picture here, where you have many atoms that are trapped in its separate potential, almost like a crate, egg crate, with some arrows to indicate that in principle they could have spin. But the sort of atoms we are talking about today are typically neutral atoms. Now, optical lattice are free of dislocation or impurities. So this, in general, is a preferred mode compared to, let's say, wires. Even in a typical electronic wire, you have lots of defects. But on the other hand, sometimes we do want to have defects, and so we deliberately add defects. There are no phonons, and yet we can engineer them. there's no long-range Coulomb interaction, although dipole-dipole interactions can be possible. We are flexible with the statistic, like I mentioned. You can use fermions or bosons. Lattice constant can be tuned, so you can tune the optical lattice. And the potential is exactly known and controllable. So it can be switched on and off and modulate. Lattice dimensionality can be chosen at will. Quasi-periodicity is easy. And also, if you need to, you can do what's called shaking potential. That means you allow the potential to vibrate in time. So what are the sort of Atomtronics applications that one envisage? It is in some sense a heavy tool, but we presume that in the future when the field is more robust and more mature, we could in principle do precision measurements. Clocks, for example, is one of the targets. We could do microscopy, probing tiny atoms and ions. You can study superconductivity and superfluidity because the atoms move seamlessly through the optical lattice. Experimental quantum logic, perhaps. We can do investigate novel magnetism, synthetic magnetic field. We could also study complex quantum system in general and macroscopic transport phenomena. Now, so how are the atoms trapped? Well, the atoms are typically trapped in what's called so-called controllable flexible potentials. And these potentials are produced by optical fields, typically, or magnetic fields that exert forces on the atoms. So it's not hard to derive that the optical dipole potential that one can get can be derived to be that given by that formula. Well, of course, gamma is the decay and delta is the detuning. And I here is just the intensity of the laser beam. Now, if you look at this particular formula, it actually is nothing more than a chapter from your electromagnetic theory, where your potential is written as the dipole moment dot the electric field. And typically, the dipole moment is proportional to the electric field. And so you will then get that the dipole potential is just minus the proportionality constant multiplied by E squared. And E squared is just precisely your intensity. So this is how this formula is derived. You can actually get from very simple consideration where you consider a harmonic oscillator mx double dot plus gamma, which is this gamma, decay mode, x dot plus omega square, omega naught square, x being equal to the external magnetic field. And so it's just a simple differential equation that you can solve. And when you solve that differential equation, you get the polarizability. And the polarizability is just the proportionality constant over here. Now, the dipole, optical dipole potential can act as waveguides and traps. You can also get it through time average optical potentials. Or you can also do these photon atom interactions through what's called spatial light modulators. So these are modulators, these are essentially design lenses that can produce high intensity at some point. But nowadays, of course, there's what's called the the DMD, those dynamic micro mirror devices, which in some sense, acts like very much like your overhead projector in a lot of cases where by changing the pattern on the overhead projector, you can allow different intensity to be acting on a sheet. And of course, there are other ways in which you trap potential simply with micro arrays or micro lenses, very much like optical tweezer. There's also another method of trapping atoms, and that is through magnetic potential. And for the case of magnetic potential, there are typically two different types. One is the Yoff-Pritchard trap, which essentially consists of a quadrupole with an axial parabolic field. The other one is, of course, the time orbiting potential or TOP, where you move a 3D quadrupole gradient field, and depending on how it rotates, you trap the atom. And I think it is allowed because of the time orbiting field, because Ernst's law theorem says that you can actually trap with just simple electric and magnetic field, static. And one of the important things in Atomtronics has been what's called the atom chip technology, which is nothing more than looking at various configurations where you design different types of magnetic field with different wires. And for those of you who study electromagnetism, you'll realize that you can actually do shaping of the magnetic field around wires. And this is precisely what you do. And these wires can be embedded into very thin slices of silicon materials and allow it to do trapping of atoms. Miniaturization is in fact one of the key things in Atomtronics for several reasons. So electronics, of course, we miniaturize so that we can get our current handphone, computers. All this require miniaturization to a large extent. A lot of work has also been done in miniaturizing optical devices. In particular, that's another area of work that I've been engaged with, which is to look at how to miniaturize the optical bench, all those devices on the optical bench, onto tiny chips that is 1 centimeter across and half a centimeter wide. And within it, you have the whole table, the optical bench. So what we are talking about in Atomtronics is matter waves. And matter waves means you have atoms, and so you need if you want to miniaturize it, you have what's called an atom chip. Now the atom chips, in some sense, trap the atoms simply from the from magnetic field. So why do we miniaturize? Because the large trap level spacing help us to suppress heating rates. So in fact, the smaller the device is, the more less power we consume. Also tailoring the resolution of potential for atom manipulation is given by the resolution of the fabrication devices. And so atoms are small, so it makes sense to have tiny traps, and therefore it's necessary to consider miniaturization. Also, fabrication nowadays is very mature, and we can do a lot of this in the fab with great accuracy. And we hope eventually that this nanofabrication will allow us to integrate with other techniques on the chip and other devices as well. Noises, of course, is one big problem in chip technology. So you have this device that is playing around onto the two-dimensional chips, but the typical resolution of the field is of the order of the distance from the field source. And so the construction of the atomic circuit at a distance no more than a few micrometers from the surface is typically required. This results in somewhat a few types of noise, and one is Johnson noise, which originates from the thermal energy. And the other one is noise that are related to propagation along the waveguide, whenever there's corrugation in the waveguide potential. So a lot of this noise will result in a loss of contrast in the interferometry. The atom optical elements that we think of are typically waveguide beam splitters, and you can see that by designing appropriate wires that carry currents and therefore design a magnetic field, you can actually persuade the atoms to move along certain path. And so this is the different geometries for beam splitting potential. For example, the picture on the lower right is actually the experimental investigation of the same thing. You can also do atom trapping in terms of toroidal structures. So these are optical traps. You can trap, imagine that there is this toroid, and then the atoms are free to move and round this toroid. Very much that. And I'll come back to that later. It forms what's also called persistent current. You can also stir it, and you see that in this particular picture, you have this gap, and this gap is actually where the light shield is. And where the light shield is, this is a moving light shield. The moving light shields move, and then it stirs the atoms that are trapped in this toroidal cavity. So you can typically design some of these traps using lasers. These are the lasers and the crossbeam. So this laser provides the planar sheet potential, the planar potential, and then the vertical laser provides the design. So sometimes we call this painter potential. So okay, so why Atomtronics? Well, in some sense, it's a revival of an idea that was realized some time ago, several years ago, somewhat like 10 years by now, roughly 10 or 8 years, by the Gretchen Campbell group, who originally was at the National Institute for NIST, Science and Technology in USA, Maryland. And what she realized was that she could observe this flow of atoms of this current within the toroidal structure. So she created a toroidal structure like so, and then she starts to rotate it with a laser beam. So think of this as a laser beam, and that's where the laser is, and then you start to rotate it constantly with time. And they were able to observe certain phenomena. In particular, they managed to observe that you could introduce angular momentum into the atoms. And the typical way to analyze it in mathematics is what's called Gauss-Pidevsky equation, which is a mean field equation that describes precisely how these atoms are propagated. And this is, some of you may be familiar if you are doing integral models. This is just the Schrodinger equation with the potential, external potential. But there's this nonlinear term or nonlinear Schrodinger equation term with the chemical potential. And that sort of wraps up the description, all the mathematics that's needed to study these ultracold atoms moving in this toroidal structure. They're supposed to have some animation, not sure if you'll see it. Can you see this animation? I hope you can.
Yes, yes.
Yes.
Thanks. Yeah, so you see that it is this from Gretchen Campbell's experiment. So they move it around, and I'll show it again. So this is where the light sheet is moving, and as it moves, you can see the density plot of the current. Now, and of course, you would like to know some effects. So what they do is that they rotate it into motion, then they superimpose with an expanding Bose-Einstein condensate cloud by allowing it to free fall. And typically, when you superimpose a rotating pattern over this expanding cloud, you will see that it forms interference pattern that shows the spokes. So if you are rotating this way, you will see that the spokes move curve in that particular direction, and so you get very beautiful star-shaped structure which you can count, and by counting you can actually know the angular momentum of the atoms. And then you can of course study those the physics behind the phase slip at the juncture where the laser is acting on. And more recently, a couple of years ago, von Klinsing, this is the son of von Klinsing, so Wolf von Klinsing, showed that you can actually stir this in the rings, and then you can accelerate it. And you can accelerate it to how fast? Well, so they managed to accelerate it to something like 16 times the speed of sound. So this is like, if you think of aeroplanes, this is about 16 times Mach 16. So it's a very fast aeroplane. So they were able to measure that speed. And the same experiment is also done by another group in France, led by Elisabeth Jacobino in Paris, ENS. And I think they have also achieved the same result. And one of the earliest papers on this topics was written by Murray Holland, led by Murray Holland the title was, this is the first time Atomtronics ever appeared on the title of a paper. And although the word Atomtronics was mentioned much earlier. So Atomtronics, the ultracold analogs of electronic circuits. And what Murray Holland did was a theoretical study in which he considered, so some of you may have, and in a separate paper, he considered diodes and transistors, where he considered a Hamiltonian. So this is not a toroid anymore, but rather atoms hopping from lattice sites in a circle. And he modeled it with what's called the Bose-Hubbard model, where J is the hopping parameter, and the U is the Coulomb factor. So this is, if you think about it, if n is 0 or 1, this term is disappears. N is 0 means you don't have this Coulomb repulsion term. But if n is 1, you wouldn't have repulsion as well, right? So it's only when n is more than 1, like 2, 3, and 4, that this term arises. So so then you get this particular term. And they consider, of course, the system in a reservoir, and they could show that depending on how you design the optical potential, you can, of course, mimic a semiconductor device. So if the atoms are all in this energy level, so there are two energy levels of the atoms that can be trapped in the potential well. So if the atoms are all in this, we call it band 1 or valence band, and atoms that are excited to the next band, these are called, in some sense, conduction band. in a nutshell. But then what you can do is that you can redesign your potential so that there are places where it's deeper, and then the energy of the atoms actually fall short of the conduction band. And so this is like an n-doped lattice. And similarly, you can redesign with a more shallow potential and then mimics a p-doped device. So this is very much like Wikipedia. I think this is from hyperphysics, where you see that you can actually engineer N and p-doped devices. And with N and p-doped devices, of course, it's natural that you can put them together and you get forward and reverse bias, very much like electronic circuits. And this is in the paper of the Physical Review Lattice. And you can also demonstrate Atomtronic battery in some sense, where you have a large pool of atom and another edge where you have a smaller pool. Now the chemical potential of the atoms will pull the atom across this optical lattice. And I think the experiment was also done by Dana Anderson's group in NIST. And so you can show that you can build simple electronic circuits, a resistor, and a battery, and things like that. So our interest, in fact, in Singapore on the Atomtronics starts with a paper in Physical Review Letters by Luigi Amico, where he showed that by passing light through an SLR, you could actually engineer layers upon layers of optical lattice. So these are like very much like interference patterns that are formed from two opposing Laguerre-Gauss beam, SLM, spatial light modulator. So you can actually have two opposing Laguerre-Gauss beam, and then you can produce them. And if you consider one of these layers, actually you can tune the distance apart between the two Gaussian surfaces. And this actually starts our first trip towards NTU site, where we discuss with experimentalists who appear to be very interested to do the experiment. And that was more than 13 years ago. And 13 years later, we still have not achieved this. So it is actually a very hard experiment to a large extent. I would say that it's not easy. It's easy to be done on paper, but experimentally there are lots of challenges. We have managed to create some nice result recently, but we are behind in many cases. Okay. So what happened? Okay. So I'll go through this very quickly, but so we considered a couple of mathematics based on two, so that there is two optical lattice spaced very small distance apart. So between the first lobes of optical lattice to, again, I said that you can do this with painted potential nowadays, and that is precisely what they're doing in the lab. You could, so this is layer A, so we call this the atoms that are moving here are labeled A. Atoms are moving on the green layers are called atom B atoms. And of course, there's the hopping of atoms from A to B and B to A, which is described by this mathematics. The rest of the mathematics are exactly the same. Now we have put in a term here, which is not part of the Bose-Hubbard Hamiltonian. And what does this term mean? This is actually the gauge term. The gauge term that describes the rotation of the atoms in that optical lattice. So we are imagining that we use a light shield and we rotate it, and that results in an effective magnetic field, U1 magnetic field, which we imprint onto the hopping term, because this is a term that describes hopping from I site to the I+1 site. And what could we do? We could show effectively that we can build single qubit gates out of the system of 2 layers of atoms flowing in both layers. The zeros and one are just persistent current, a current that's moving in one direction or the other. And we also could show that you can build 2 qubit gates. I'll skip those details. And by engineering the potential so that some of this potential are of higher level than others. So this is actually experimental potential that we have created. But to trap the atoms and allow it to flow is another thing. You can actually mimic what's called atomic squid. So these are superconducting quantum interference device. And so with the aquid atomic rather than squid, this is Atomtronics quantum interference device. We could show various patterns that allow us to study superposition to time of flight experiment. And also we expect it to be able to study the chirality of spirals. And then, of course, very beautiful patterns can be studied simply. And this was a paper led essentially by my former postgrad student, but now at Imperial College. And 2 high school students at that time. So this was 2018 when it was published, but these students were doing in 2016. So it's something like 8 years ago, 9 years. Well, at least 2015 or 16. So at least 7 years ago. And so Joel is now doing his PhD at Singapore University of Technology and Design, SUTD, and Mark is at MIT. So Rainer is the lead experimentalist, and you can produce nice patterns. And it appears in the news simply because the newspaper wanted beautiful pictures. And then you can increase 1 link to 3 links, and you produce what's called an AC squid rather than a DC squid and things like that. So a more versatile squid. Now, we can, of course, also mimic what in cavity QED or circuit QED they are doing. In circuit QED, you can build atoms as well. But in circuit QED, the atoms are actually artificial atoms in the sense that each one of these atoms is made up of effectively a capacitor with an inductor. So when you put a capacitor across an inductor, you actually have a resonator. And then you can put lots of resonators together and they serve as artificial atoms. And we can, this circuit with artificial atoms and then real magnetic field can be produced what's called fluxonium, which they use and apply it for certain applications. And so what we did was that we consider what's called a Mexican hat potential, where if you look carefully at this array of painted potential, you have rings, toroidal rings. So these are no longer optical lattice with sites, but toroidal rings, very much like Gretchen Campbell does, except that we have many, many of this. And then in the middle, there are a high potential so that the atoms cannot just simply move across. So of course, you can lower that potential, but in any case, these are even higher by the side, so it looks like a Mexican hat. And atoms can move, we allow the atoms to move from hats to hats. And very much like a classical hexagonal lattice, which you can mimic a classical, what's called a Kagome lattice. And you can study some of the potential and results. And another aspect of physics that you can study with Atomtronics is has its motivation in what's called so-called the whole branch of what's called Mesoscopic Physics, which was started actually in some sense by a group of people in Israel, in particular by Joseph Imbri, who passed away recently, a couple of years ago. And what they did was that they consider tiny electronic circuits where the electrons can move in circuits like this and recombine. And then they look, depending on the magnetic flux in the middle, it affects the transmission of the electron. And so if you look at the transmission of the electrons at the other end, you get this interference-like pattern, okay, depending on the flux. So by changing the flux, you can actually fluctuate and vary it. And so we allow ourselves to do the same thing, exactly the same thing, but more user-friendly in some sense with atoms. And in atoms, the way we envisage is a big reservoir of atoms on one side and another reservoir which is depleted with atoms. And then we try, there's a natural chemical potential, and the chemical potential pushes the atom across this structure. Now there is this magnetic flux that we need to, and that we do with laser light stirring. So we literally stir the condensate. And so the whole idea is that we can study interactions due to what's so-called a Aharonov form effect. And also we can study time dynamics and think of possible application. Now this is indeed a very useful device to think about. Atoms that are coming in are split into two paths. So this is like a beam splitter here, and also a beam splitter at the other end. And then you go, of course, through the two channels. The beam splitter here with another beam splitter is sometimes, this whole structure is sometimes called a Mach-Zehnder interferometer. So the way to study it theoretically at least is we have this rotating potential here. You can see this flux. Sometimes we call this the power substitution, and with the Coulomb potential. And then we have from the source to the first site, and from the last site D to the drain, okay, or L upon 2, sorry. So if there are L sites here, then this diagonally opposite will be L upon 2 site. So that attached to the drain, and the 0 site is attached to the source. And then you can see animations of that. You can see as time goes by, the atoms go from left to right, simply due to the potential. And then if you switch on a different flux, essentially a different stirring, you get a different pattern. So I'm not sure if you caught that. Right? Anyway, one can look at different patterns by varying the flux with this is time axis. And then you see, of course, this repeating patterns. This is the pattern at the source, at the ring, and at the ring and at the drain. Provided, of course, the couplings are weak. That means J is the hopping, and K is the atom-to-atom coupling. And if the atom-atom coupling is strong, then you see a lot more chaotic patterns. And yeah, I think one can study it in more details in that sense. So the same thing is you can study parity. I'll skip that. And you can, what happens is that you, strictly speaking, you have to study what's called an open system approach, where you study master equation and you look at atoms hopping into the ring and then recombining at the other end of the interferometry. But we could consider these are no longer atoms, neutral atoms or bosons. We could also consider fermions. What happened if instead of boson, there are now fermions? Now, fermions, like you know, obeys Fermi rule. I mean, there's this exclusion principle. So they try not to hop onto the same optical lattice. Or we could also consider, at least theoretically, you can consider anyons. And you see that if you look at the current that flows through the lattice, the boson currents never gets to zero. This is the boson. But the fermionic one at certain rotation can actually diminish to zero. And of course, one can think of cool devices with that. So in some sense, if you plot one axis, the fractional statistics, and the other axis, the rotation, you can manipulate different couplings. At a strong coupling regime, you can actually manipulate, observe the different type of currents. So the color here just represents current. The red means strong current. The blue means very weak current. And then you can study different geometry. So this was done by Tobias Hau, who is now at Imperial College, as I said earlier on. And you can study atoms hopping into a Y junction. And actually, this is precisely this portion in more detail. And then you can see that by studying that, you actually get an intensity pattern that locks below, very negative, that goes below the axis. And this is somewhat reminiscent of what's called Andreev-like scattering. And you can, of course, add shaking potential. That means at different times, the potential is at different slot potential. And with a shaking potential, something else can happen. You can actually show very much that you can create, depending on the statistics, you can actually create what's so-called noon states and do what's called so-called topological pumping. And in particular, this is like 3 particles are coming in. So imagine you have 3 particles coming in. Then you can show that in certain regime, okay, in the convex, it depends, of course, on the energy landscape that you are applying. If you are 3, 0, 0, meaning the 2 fork legs are 0 at the beginning, will become a 0, 3, 0, 0, 3 state. We sometimes call this a highly entangled state called a noon state. And 4 will become 4, 0. So you in some sense, you get a noon state for free, which in optics is quite difficult. But if it's convex, of course, you get slightly different picture. You get product states in some instances. You can also consider 2 species operating in this configuration. And then you can consider ring ladders. And in ring ladders, you find that you duplicate what's called the vortex Meissner current. So this is allowing the 2 rings, top and bottom, and then you twist it by a particular angle. Then you see that they either get the vortex phase, meaning that they rotate among them in separate wells, or they start to hop between, sometimes called avoiding the. So we call it a Meissner's phase. And then depending on the twist, if they are aligned, you get symmetrical. The vortex phase is essentially covering the region when the phase is precisely a half pi. But when you start twisting it, this picture goes up. The more you twist, the more it goes upwards, and the vortex phase essentially shift upwards. And then you can study it with different different interaction strength as well. And you can also consider a lot of these atoms that are trapped in this toroidal thing, and then you bring along an empty cavity and allowing the rotating current here to leak across into the waveguide. So of course it makes sense. Eventually, some of these atoms will start to leak through or seep through this potential. And depending, of course, on whether you rotate it right or left, you detect a slightly different sort of current, because if you rotate it this way, around this way, then the current tends to go this way, more or less common sense. But nevertheless, this device allows us, in principle, to have a tiny device that can detect rotation of some sort. Now in the lab, some of this equipment, if you have seen superconducting qubit, you will see this device, which is really a fridge. So a lot of this has to be done at low temperature. So that's why you also will see fridges at Atomtronics in Atomtronics circuits. This is the circuit at NTU, where we allow the atoms to move into the atom trap region. I think there are a lot of literature if you would like to. So one of the oldest literature was published several years ago, where together with Luigi and Gerhard and Malcolm, we put forward a focus issue on Atomtronics enabled technology. You can read, go to that site, and then you can actually read various papers submitted by various people. More recently, a couple of months ago, we have also published a roadmap on Atomtronics in AVS Quantum Science. And so you can read about this in the literature. We have this pattern, which is created for our biennial workshop in Bernasque. The last one was supposed to be held last year, but it was held online actually. Yeah. This is another piece of work which we have submitted. So it's more like a review paper. In fact, much of today's talk is based on this paper. So this is done with Luigi, Dana Anderson, Malcolm, John Philip, and Anna and Prof von Pinsing. It should be published in Review of Modern Physics. More recent Atomtronics devices, well, aside from those that we have looked at, people are now interested in how to put some of these devices, in particular, the group by Gallagher has been looking at how to launch into outer space with these tiny atom circuits and measuring the rotations. So they are quite serious about that, and they would like to see bosons and condensate in space. A lot of this field of Atomtronics is blue sky at the moment. But I would like to remind you that in the 60s or even in the early 70s, a lot of our lasers and optical fibers and integrated circuits were basically blue sky research. Nobody knows where they were going, but nevertheless, things were being explored at that stage. And nowadays, we know that all these devices have contribute a lot to global communication network. So, and we have a future. So is there a possibility? What is the grand scheme of things? Are we replacing electronics with Atomtronics in the future? Well, if that were the case, we will be completely mistaken, because it is impossible to replace electronics with Atomtronics. Electronics are cheap and handy and just simply plain simple easy to manipulate. You don't need low temperature, you need none of these effects. But what can Atomtronics do? Well, we don't replace electronics. We may want to think about some devices that mimics electronic circuits. But we would also like to see if we can do something that people in spintronics have tried to achieve but could not do it. And one is what's called the data transistor, which is a spin transistor. In fact, there is a scheme that in Atomtronics that allow you to do that, although demonstration of that is still some time away. We would like to the Atomtronics to interface with circuit QD. After all, circuit QD is also contained in this refrigerator. So you can have Atomtronics happily interfacing with artificial atoms, real atoms with artificial atoms. And they can combine effects, and we just don't know what new synergy comes up. We could have better sensors and imaging devices. We could do simulators, and this is the area that Bill Phillips has always been interested in. We could do microfluidics, which is an emerging area. So you replace the fluid by atoms, matter waves. And we could also think of replacing some of the optical device with atoms. Now, Wolfgang Katterle said many years ago that people in the entertainment industry didn't discover laser for DVD or Blu-rays. It was the work of scientists, and dentists didn't discover X-ray for improved medical imaging. That, again, was the work of scientists. And Michel Lukin also said that not only should scientists be allowed to investigate technologies, they should be encouraged to do so, because improved clocks are now an important part of driverless system. Improved sensors have made it easier to find cancer and so forth. And finally, I quote from Serge Ahosh: "It is hard to make prediction, especially about the future." He attributed this statement to Niels Bohr. But one thing he said for sure is that without basic research, without blue sky research, without novel technologies cannot be invented. And the past has teaches us that wonderful application always emerge serendipitously from blue sky research. I need to thank many people for collaboration. This is not an exhaustive list. That's part of the pictures of experimentalists and theories. Let me do some advertisement. I'm also an editor in AAPPS. Hisham has published some articles in AAPPS Bulletin. But now AAPPS Bulletin has got serious. It's now managed by Springer Nature. And I do encourage you, if you have good ideas, to submit your articles there. I'm been editor of Quantum Science and Technology for some time. It's got pretty good impact factor. And a lot of topics on atom science and technologies are published there. This one, I've been there for years, don't know, donkey years. And impact factor is not as good, but certainly we do welcome, if you are not concerned with the impact factor, we do welcome you to submit your articles there. And thank you very much. Thank you.
Yeah, thank you, Prof. Kwek.
Thanks.
Quite. So
I can stop sharing, I guess. Any questions?
Yes, doctor, I have a question.
Maslian.
May I know what is the amount of the magnetic field applied in the experiment?
In the experiment, the magnetic field is not terribly high, but it's several gauss. Yeah. So it's not high intensity magnetic field though.
Oh, all right.
Yeah, into the into the Tesla regime.
You managed to observe the, I don't know, bomb oscillation? Because last time we
No,
were
no,
looking.
no, no.
Yeah, because I tried to apply
We,
up to 60 Tesla, but I still couldn't observe it.
okay. Yeah, it's not so easy.
Yeah.
Yeah.
All right. Thank you.
I think you need low temperature as well. Yeah,
Sorry?
but you need some low temperature to see interference pattern.
Yes, we run it at 4 Kelvin, but still couldn't get it.
Yeah, I think one of the group members have got some interference pattern. But it's not something really. So I'm trying to show you his WhatsApp messages. Can you see that? So he was very happy with that. Can you see any interference pattern? Maybe, yeah. So they were very, very excited. The experimentalists were jumping up and down with that saw picture. So this is, if you observe carefully, especially with the side profile, you can see some interference patterns. Yeah. But I agree, you have to try very, very hard. And it's not so easy to get. I would say that this guy got it after 7 years. So don't give up.
Okay, are there any more questions? You can raise your hand or type in the chat if you want.
Yes.
There is a question in the chat.
How do I get the chat? Oh, yeah. How is this Atomtronics system differ with optomechanics system? What extent? Well, optomechanical systems are cantilevers. So the cantilever, of course, is a macroscopic device. It's not atomic. So you don't get coherence in that sense. But of course, nowadays you can build smaller and smaller cantilevers. By that, cantilever is still made up of many, many atoms. So we are talking about typically about so what we can do when we are talking about cantilevers is to use that as a medium to mediate interaction between so-called atoms. And in many cases, it's NV center of diamonds. You put 2 diamond NV centers on the cantilevers and then allow them to interact through the cantilever, and hopefully the atoms get entangled to each other and talk to each other. So that is somewhat like as quantum as you can get. Otherwise, if you study the cantilever itself, is a macroscopic object. But even though it's a macroscopic object, there's nothing to prevent you from studying classical oscillation. Now, classical oscillation, you might think, oh, is a topic that doesn't deserve research. But it turns out that in recent years, oscillations of any kind, especially nonlinear oscillators, have ignited a lot of excitement in terms of amplitude depth and synchronization. And it's a big topic. Yeah. In fact, there are people who have built a career out of that. Very interesting. Yeah. One paper was actually published in 2005 to be precise, where they wrote about a cantilever of some sort, but this is a huge cantilever. It's the London Millennium Bridge. So if you are in London, you will walk across this Millennium Bridge. It turns out that on the day of opening of the bridge, too many people walk through the bridge. And then in order to balance themselves, it's actually a swaying bridge. So it starts to sway side by side. So the people, in order to balance themselves, actually synchronize themselves with the swaying. And that creates a big big, it's not resonance, but it creates a big synchronized effect, which actually endangered the whole bridge. So the bridge was then closed for several days after that. And 5 years later, there was a piece of paper in Nature that analyzed this effect. It's called critical resonance, critical synchronization. And that was published in Nature. So it is an interesting phenomenon. So.
Okay, any more questions?
I have questions. Hi, Prof.
Hi, Nerissa. Yeah.
You're talking about this ion trap, like with toroidal trapping. Can we have like something else like spheroidal like trapping, for example? Is it possible or?
You mean in the cloud?
Yeah.
Yes, a cloud has always been investigated. In fact, when I talk about the data transistor, that was the proposal was through a cloud. So you transfer the spin, the fermions from one side to the other side through this cloud, and effectively you sometimes can do it with cloud, but more interesting physics sometimes is done with just two-dimensional. Already in 2 dimension, there are so many geometries that we can play with.
Okay, all right. Yeah. Thank you.
Okay, any more questions before I get to my own questions? Maybe I should first. In the paper, the review paper that you give to us the reference, you mentioned about the complex geometries. What precisely is actually meant by that?
Basically, I think it just means that I think you're referring to the wire geometry.
Yeah.
Yeah. So you can actually set up very complicating wire structures and then produce. So there is in fact a whole industry of people who actually just do classical electromagnetism. Look at how wires, different configuration of wires set up different potential. This is of high interest to people in Atomtronics. There's nothing quantum about it, but the structures, if you can reproduce, or you know very well how to design magnetic potential with different profiles. Typically, this is of great interest to people in Atomtronics.
Okay. I remember once Professor Miniatura came to UPM. I was describing my work on this hyperbolic surfaces, and he was mentioning something about we can easily create those. Is that
with light shield? You can with a light shield, with a light modulator, spatial light modulator. You can create any shape you like.
Okay.
Yeah.
So
and then you play with it.
You could in principle get all those different hyperbolics.
That's right.
But these are mainly in it's not part of the Atomtronics, or is it?
Well, it depends. If you play with that light, so you could only create a light structure, a profile. But if you can interface that with atoms and look at the motion of atom in that light, in that traps, then it's part of Atomtronics, because you are interested in dynamics of that.
Okay.
Yeah. So why in principle do you want a specific hyperbolic structure? And typically the way I think about it is in gravitation. In gravitation, there are lots of structures that are hyperbolic in geometry, and we would like to study what happens to atoms when they go across this or traverse through these hyperbolic surfaces. And so in some sense, you're studying gravitation. In fact, what I didn't mention in Atomtronics was that there is, in fact, a whole group of people in the United States, in Maryland, who are interested in studying gravitational phenomena using Atomtronics.
Okay, anyone else has any more questions before we close the recording? Then we can have informal discussions. Anyone else? Maybe for the students, for those who are interested in Atomtronics, any reference that you would like to, introductory reference that you would like to suggest? Is my mic up? Did you hear me?
Somebody is trying to, Pakshan, you just unmute yourself and say something.
Oh, okay.
Oh, okay. Just kind of like an outsider question. So, like, what do you think about like maybe the current challenges in Atomtronics, and maybe what do you foresee like the future breakthrough of this area?
Current challenges, plenty. It is still very raw in a lot of sense. If you think quantum computer is still very far away, this is even further. That's why I tend to call this blue sky research. The challenges are huge, but some people are very optimistic, and one of them is Bill Phillips. He's always very keen to promote his field. Not sure if you know who is Bill Phillips. He's this Santa Claus guy, Santa Claus looking guy. Nowadays, he looks more and more like Santa Claus, who got his Nobel Prize 20 years ago for atom trapping. And so he's very optimistic about the prospect of having Atomtronics and devices to explore, mainly as a quantum simulator to a large extent. But there are lots of challenges. Already you saw the interference patterns. It took us nearly 7 or 8 years to achieve that. And that's just combining two clouds or atoms to produce interference. And we have not even done a RNL bomb type of experiment. It's still very far away. I've almost lost hope. Maybe 10 years after my retirement, we will achieve something, but still it's very hard. So in particular, there are other technologies that are proven to be more useful. I hope those technologies will take over some difficulties that is currently faced by Atomtronics. And one of them is in quantum information, you have what's called building quantum computer out of neutral atoms. So it seems like you could also do that with Atomtronics. I mean, you could import some of the ideas from Atomtronics or export some of the ideas from Atomtronics over there. And then you can see that some of those ideas might be more easily done there. Also, Ripple atoms is another area. Ripple atom so far has been classical, on the classical level. The interactions are Coulomb forces. But nevertheless, it's been proven to be more and more plausible and feasible in the last few years. So there are people who try to explore Ripple atoms. Maybe these people are likely to move, if needed, into Atomtronics. So challenges, I would say, are huge. Even studying the magnetic field is a big thing in this technology. So, and it's not something that some of you can, it's a bit boring, okay. Yeah, the science is a bit boring. what do? You use Biot-Savart's law just to design the magnetic field. But nevertheless, once you understand it in detail, your skill set becomes very useful for people in Atomtronics field, because you're going to build, of course, similar circuit, but not big wires circuits, but tiny wires in tiny little chips. And we want to trap atoms, of course. Ultimately, the idea is to trap atoms. So in terms of current challenges, there are some progresses. With simple devices like toroidals, people have observed a lot of things. Even looking at toroidal atoms moving in toroids, and then bringing an empty waveguide next to it, nobody has done it yet. So it is still moving something else, some other traps close to an existing trap is still a big problem. Moving atoms into the trap is also a problem, very much a problem. So there are a lot of problems, both in terms of cryogenics and also in terms of trapping. So lots of the breakthrough was the last breakthrough was maybe by now nearly 10 years ago with Gretchen Campbell, when she discovered that you can actually do rotation of this post-Einstein condensate. More recently, of course, is von Klinsing, Wolf von Klinsing, where he showed that you can accelerate it to max 16. So 16 times the speed of sound in that medium. And that is quite, nobody has gone into studying how to accelerate it. And for the last 2 years, the COVID has not helped us. The lab in Crete, von Klinsing's group, has closed down, and basically closed down. And I'm not sure how long it will take for them to restart the whole program. So labs are also affected by COVID as well for the last 2 years. So breakthrough in terms of future, I think the next nice thing to see would be some fundamental science that you can get by looking at some of these atoms moving in some engineered or designed trap. So this would be the next breakthrough. And looking at some of the more fundamental phenomena, you can actually put a mixture of boson and fermions. I think there's a group trying to do that, but so far not too many results have come from that lab. Does that answer your question? I hope it does.
Yeah, I think more than enough. Okay, thank you.
Thank you. Any others?
Yes,
I don't know if there are new students in the group. I'm sure there are. Bakshan is no longer a student.
anyone has any questions before we move on to the more informal session? Otherwise, let's thank Prof. Kwek.
Thank you.
Okay. And I will stop the recording now, and then probably we can have more informal interactions.